Today I'm going to talk about some of our recent work on learning-augmented algorithms applied to energy systems, sustainable computing, and so on. And this is all joint work with my many great collaborators, some at Caltech and many elsewhere as well. So during the talk, please feel free to raise your hand, interrupt with questions, and I'll also do my best to monitor the Zoom chat for everybody online. So my work is motivated by one sort of fundamental observation, and that's that uncertainty is the key challenge in sequential decision making. So regardless of what application we're looking at, if we're looking at sustainable, it's not changing for the Zoom people? So screen sharing is paused. Okay, so if I go full screen at start, it like pauses the Zoom share.
I see. Yeah, I think you're just sharing your current screen on Zoom. You might want to share your entire desktop.
Oh, okay. Okay. I assume this is going to work now. Okay, so uncertainty is the key challenge in sequential decision making. So regardless of what application we're looking at, if it's in energy system operation, there's variable renewables, and we can't forecast well what generation is going to be in 5 minutes. In video streaming, there's uncertainty in terms of what bit rates are going to be for download speeds in the next 5 or 10 minutes. In data center operation, there's uncertainty around what carbon intensities will be for electricity generation, job demand for running on the data centers, so on and so forth. And in particular, I think a lot about energy system and sustainability applications, and uncertainty poses particularly difficult challenges here. So in the energy transition, there's a lot of increased renewable energy coming on the grid, and this is characterized by uncertainty and variability in terms of generation patterns. And this motivates questions like how should we optimally operate these generation resources, both existing resources and new resources like battery storage or grid inverters optimally in this new regime? And how do we do this optimal operation while ensuring system safety and reliability when we're faced with this increased uncertainty? Because it's not enough to just add a bunch of resources to the grid. We also want to make sure that we're able to meet demand and we're not going to have large-scale blackouts. So as many of us know, we are here at an AI seminar. AI and machine learning can help with a lot of applications to decision-making under uncertainty. And in particular, the past 10, 15 years, we've seen AI and machine learning achieve state-of-the-art performance in domains such as game playing, self-driving cars, data center cooling, and power system operations. But there's one big problem with deploying AI and machine learning tools, black box, to high impact problem domains, and that's that they don't come with a priori guarantees on their performance. And so there are examples from the literature where if you perturb the input to a classifier just a little bit, it can misclassify a dog as an ostrich. And these sorts of adversarial attacks on classifiers are not limited to just toy examples and classifying dogs, but there's also examples where if you make the image seen by a self-driving car just a little bit darker, instead of going left, it'll decide to go right. And so this highlights the challenge when we're trying to design safe and reliable machine learning tools for realistic high-impact settings. And this is also a problem in energy system operations. So this is some work showing that if you just perturb the temperature forecast profile just a little bit for like an energy system dispatch application, it can lead to very significant amounts of load shedding, so blackouts on the grid. And so basically, one of the main motivators of my work is how do we design safe and reliable machine learning algorithms so that we don't end up deploying something that we don't understand and leading to a large-scale blackout. And so, in other words, how do we take advantage of AI and machine learning while ensuring worst-case performance guarantees? And in this talk, I'm going to be talking about some of our work on doing this for online optimization, and in particular, designing algorithms that take as input black box advice. And in addition, I'm also going to highlight some first initial steps toward going beyond the black box advice regime and thinking about how we can integrate uncertainty quantification into online decision making. All right, so without further ado, I'm going to start talking about black box advice and online optimization. So the general problem setting that I'm going to be talking about is online optimization with switching costs. And you can think about this as a game between an adversary and a decision maker, where at every time step of some sequential problem, the adversary gives you a function ft mapping from some metric space M to the positive reals. And in return, the decision maker has to choose some decision xt in that metric space. And they pay both the cost of that decision on the cost function handed to them by the adversary, as well as some switching costs of changing from their previous decision xt minus 1 to their current decision xt. And the cost given to them by the adversary is called the hidden cost, and then the switching cost is called the switching cost. And at the end of the day, they pay a sum over all of the costs that they incur instantaneously in each round. And this problem has gone by many different names in the literature, depending on which community you're in. So in systems, it's known as smoothed online optimization. And in the theory literature, it's also known as function chasing or metrical task systems. And I'm going to mostly use this last name throughout the talk. And the typical goal when designing algorithms for online optimization with switching costs or metrical task systems is to design algorithms that achieve the smallest possible competitive ratio. And so this is the worst case ratio in cost between whatever algorithm you've designed and the offline optimal algorithm that knows all of the cost functions in advance. So the offline optimal algorithm has no uncertainty, whereas you're making decisions online only with knowledge of the current and previous cost functions. And it's worth noting that in certain cases, you can benefit from randomization for online optimization, in which case this numerator just has the expected cost of your algorithm. So one very classic example of metrical task systems is known as convex body chasing. And this is related to a lot of practical applications in systems and data center operation. So in this case, the metric space in question is some n-dimensional vector space. And then the functions that we receive at each time are some indicator of being in a certain convex set. So what this looks like is the decision maker starts at a certain point, receives some convex set, and then has to move to a point within that set. And then they receive another set, and they have to move to a point within that set. And they receive another set and have to move to a point in it. And at the end of the day, they pay the total cost of all of these distances that they've moved at each time. Now, the offline optimal knows all of the bodies in advance and just chooses the shortest path that passes through all of them. And this is deeply related to the more general problem where you're chasing convex functions. So instead of just trying to move to within sets, you're faced with some general convex function. And if those functions are something like fuel cost and the switching costs are something like ramp costs, this is an energy system operation problem. And there's been a lot of work over the last, I think, nearly 30 years in metrical task systems, and as well as a lot of significant recent progress on algorithms and upper and lower bounds. So in particular, some of the original work was on deterministic algorithms, where Borodin showed that the optimal deterministic competitive ratio is 2n minus 1 on an endpoint metric space. And a line of work with Bubek and his co-authors showed an upper bound of log squared n for the randomized case, as well as an existential lower bound showing that this is tight. Now for convex function chasing, yes?
Just to be clear, this is for the general version, not the nested version.
Yes, yeah. So this is for the general endpoint metric space case with any arbitrary functions. For convex function chasing, so the case that I just showed the example of, there's a recent line of work also by Bubek and Selke and co-authors, culminating in a O of n competitive algorithm for n dimensions. And there's still some question as to what the optimal competitive ratio is. I think it's resolved up to log factors for LP norms in the nested case, where the bodies are sort of shrinking. But for the general case where you can have any convex functions, the best known upper bound is O of n, where n is the dimension. And then there's this lower bound that's like square root n for the Euclidean norm.
And so n is the dimension of the space, so it's 2 in the previous example, and the number of convex objects.
Independent of the number of convex objects. There are tighter bounds for the Euclidean norm that depend on the number of time steps. But there's some uncertainty here between the nested and the general case. But in general, the tight bound is the linear in n. All right, and then there's also a lot of special cases of metrical task systems and convex function chasing. So depending on what assumptions you impose on the cost functions, you can get dimension-free bounds. So for example, with alpha polyhedral costs, which are convex and they have some unique minimizer and they grow away from that minimizer with some slope that's lower bounded by alpha, you can get a competitive ratio that's like 1 over alpha. And there's many other different variations of this. And one other relevant line of work is if you use look-ahead predictions, then you can get competitive ratios that will decrease in the number of perfect look-ahead predictions that you have. And MTS also has many applications. I've mentioned some of them previously, but they include data center right sizing or geographical load balancing, where here the costs are the cost of operating a certain number of servers, and the switching cost is the cost of turning servers on and off or migrating jobs from one location to another. Electricity generation, as I've mentioned before, networking, video streaming. So here you have some cost for the quality of the bit rate that you're serving, but maybe there's a switching cost for penalizing switching between different bit rates, control, so on and so forth. Now, the particular model that we look at in our work is motivated by this observation that traditional algorithms for metrical task systems and convex function chasing are worst case in nature. So the competitive ratio is a worst case metric. You're looking at the worst case problem instance. And also a lot of these competitive ratio bounds depend on the dimension or cardinality of the space. So they depend on the number of points in the metric space or the dimension. Now, on the other hand, in real world problems, we have access to data that we can train machine learning algorithms on. We can just train a black box RL algorithm and maybe that'll perform better, and oftentimes it will. So the model that we use is we have some advice algorithm, and this can be any algorithm, but we'll think of it as the machine learning algorithm giving us an advice recommendation that every time we should play some decision AT. And so at every time step, in addition to getting this cost function from the adversary, we also get this advice recommendation. And in particular, we're not going to make any assumptions on what this advice is. So we're not going to assume that it's a particular machine learning model. It's just going to be black box. And so this leads to some behavior in the proofs where we really need to assume that this advice is adversarial, because we don't know. There might be adversarial attacks or distribution shift. In the most general setting, we can't really reason about this. And so it's good to think of it as adversarial, and we want to try to get trade-offs where if the advice is performing well, then we have good performance, but then if it is bad, then somehow we still have a bounded worst case guarantee. So in particular, the types of guarantees we're looking for are consistency, where we want some sort of competitive guarantee against a black box ML advice algorithm. And so throughout, I'm going to refer to this advice as just adv. And we also want some sort of robustness guarantee, where we have a bounded competitive guarantee with respect to some traditional robust algorithm. And in general, this is just going to be your favorite algorithm that you've picked up off the shelf. And in particular, we're going to look for tunable trade-offs because we don't necessarily want to exploit the advice, but expose ourselves to a really big downside loss. So for any epsilon, we're going to try to get a guarantee that says we're 1 plus epsilon competitive with respect to our ML advice. And in return, that's going to give us some degree of competitiveness against our robust algorithm. And this paradigm of designing robust and consistent algorithms has seen a lot of recent interest in the online algorithms and ML communities. It's known as Algorithms with Predictions and has been studied for tons of problems. And this website is a really good compendium of all of the recent papers in the last 5 years looking at this direction. I think there's something like 200 papers there. So intuitively, what we're doing with robustness and consistency is we have these two different regimes, where on the one hand, our ML algorithms will typically have pretty good average cost, so low average cost. But on the other hand, they don't have good worst case guarantees, so they expose us to this large downside risk. And on the other hand, traditional algorithms are not taking advantage of the data that we have, and so they might have poorer average cost, but better worst case guarantees. And so in learning-augmented algorithms, we're really trying to bridge this divide between these two regimes and get algorithms that can have the best of both worlds. And so there are two equivalent views to this. One is we're endowing machine learning with guarantees to get reliable or robust machine learning. And another perspective is that we're going beyond the worst case of traditional online algorithms using advice from machine learning. And this is sort of an area of interest in algorithms, which is going beyond the worst case assumptions, which are often used. So to make this tangible, a 1 plus epsilon consistent algorithm, if epsilon is small, is going to occupy a regime that's close to the ML advice, where it has good average case cost, but maybe has poorer worst case cost. But on the other hand, if we tune epsilon to be larger, then we should end up somewhere closer to the regime of traditional algorithms, where we're taking advantage of the advice a little bit, but we still have better worst case guarantees. And the specific approach that we take, where we have this advice and we have a robust algorithm, lends itself to a meta-algorithm approach, where really we're just taking the decisions made by the robust algorithm and the decisions made by the black box advice algorithm and combining them somehow to get another set of decisions, XT. And this will be how we design our robust and consistent algorithm. So there are some previous results along these lines, and I'll just mention a couple of them. So Antioniadis and co-authors, I think in Nurix in 2020, gave an algorithm that gave a deterministic 9 consistent and 9 robustness guarantee. And this was using a classic problem from the TCS literature known as the CalPath problem. And they also showed that a variant of multiplicative weights can achieve this guarantee. That gives you something like 1 plus epsilon times the better of the two advice and robust algorithms, plus this additive term that depends on the diameter of the space and inversely on epsilon. And then we also had a paper in Colt in 2022 where we gave a deterministic 3 plus epsilon consistent algorithm that was also 1 over epsilon squared robust, as well as a lower bound showing that this is the best that you can do for the class of algorithms we were thinking of, which are like switching algorithms that just switch between the advice and robust. And we also gave, for convex function chasing, a root 2 plus epsilon consistent algorithm that achieved 1 over epsilon squared robustness. And so these prior works leave open the questions of how do we get diameter independent algorithms for general MTS? So in particular, this bound looks good because you have the 1 plus epsilon, so you're getting close to whatever the better algorithm is, but you need to know the diameter of the decision space in advance. And it also scales poorly with 1 over epsilon. So even as you're taking better advantage of the advice of the robust, you have this 1 over epsilon. And in addition, it's not a very tunable trade-off. So ideally, we want like a 1 plus epsilon for any epsilon and then some sort of robustness in return. And then lower bounds. It's not known what the optimal trade-off is here. So we proposed an algorithm, and this was in AI Stats in 2023, which we called the DART algorithm. And I won't go into tons of detail here, but the idea is you spread the weight probability mass between your advice and your robust decisions. So you maintain some probability weight lambda over time, and then after you observe the cost function at each time, as well as the advice and robust decisions, you update lambda based on some update rule. And the idea behind the update rule is that somehow you're going to move toward the advice when the robust is performing relatively poor compared to the advice. And then you're going to decrease the weight you assign to the advice when the advice is not performing as well. And the manner or extent to which you decrease that weight depends in this sort of complicated way on the cost incurred by the advice and the distance between your two decisions, and so on. And then at the end of the day, you play one of the two decisions, so either the advice decision or the robust decision, with some probability that depends on that mixing weight. Yes?
So as you're going along, you're making decisions based on the advice you're getting from the sources. And you see what happens. You get the counterfactual results. What would have happened had you taken the other advice? Can you figure that out? Or
You do not. There's some implicit assumption here that the decisions that you make don't necessarily influence the path of the problem. So you're not necessarily comparing yourself in performance to that counterfactual, but you're comparing yourself against sort of the realized problem instance that you see.
well, I might come back to the question later on.
And right, so this is the idea behind the DART algorithm. You're spreading your probability between the two algorithms, advice and robust, transferring weight carefully. And what's nice is that consistency is easy to get out of this. So this is designed to maintain 1 plus epsilon consistency by definition. And then the only hard thing is showing that you can actually achieve a good robustness bound relative to your robust algorithm. And so we're able to prove this performance bound that says for any metrical task system and any epsilon greater than 0, DART achieves 1 plus epsilon consistency and robustness that is exponential in 1 over epsilon. And as I just said, the idea behind the proof is that consistency is easy and you get it for free. And on the other hand, for robustness, you need to bound how far astray bad advice can take you. And so I'm just going to give a little proof sketch of the robustness guarantee. So when lambda is 0, that means that we're assigning full probability mass to the robust decision. And so if we're starting at lambda equals 1, if we're starting at the advice, we can ask the question, how much cost can our algorithm DART incur before we end up back at lambda equals 0? So before we're back at just following the robust. Because when we're at the robust, we're fine, we're safe. And so we'll sketch the proof for the simple case where DART is following the advice from the very beginning of the problem instance. And if we look at this update rule for lambda, there are two cases. One is if the robust algorithm's cost is greater than some order epsilon fraction of the advice algorithm's cost, then we just continue following the advice. So lambda is 1. Otherwise, we decrease lambda, and the amount that we decrease lambda is roughly proportional to an order epsilon times the advice's cost divided by the distance between the previous advice decision and the previous robust decision. And so if we sum this update rule over time, assuming that it's only going to the second case, so somehow the advice was good to start off with, but then it was bad, then we end up with something that's roughly 1 minus order epsilon, sum of the fractions between the cost incurred by the advice and the distance between the advice and robust decisions. And so if we want a sufficient condition for when lambda is going to reach 0, this is equivalent to this sum being at least order 1 over epsilon. And so then we're able to prove in a lemma this sort of nice inequality, which is a generalization of the lower bound on the harmonic series. So if you assign all of the yt's equal to 1, this sort of looks like saying the harmonic series is greater than log n, or log tau in this case. And so with this generalized inequality, if we set the y's correctly to be equal to the cost of the robust decision and the cost of the advice decision, then we can lower bound the sum that we needed to lower bound by a sum that depends on the cost of the advice. And then we bound the distances between the decisions in terms of the cost of the robust and the advice, and then lower bound this by a log term. And this will be at least order 1 over epsilon when the cost of the advice is sufficiently large. So in particular, when the cost of the advice is exponential in 1 over epsilon times the cost of the robust. And this is the main idea behind the proof. So once the advice's cost reaches this threshold value, we know that DART, our algorithm, has to be following the robust. And so this is the worst case instance. And for the remainder of the time, it's just following the robust, and so we're fine. And so then if we apply 1 plus epsilon consistency to this, we get the order exponential in 1 over epsilon robustness. So when I first showed the theorem, you might have been thinking, okay, we got 1 plus epsilon consistency, so we're able to take advantage of ML, but then we have this exponential in 1 over epsilon robustness. Like that seems really, really bad. Because even if we want to get, say, 2 consistency, we're still going to be exposing ourselves to a really, really bad downside. So is this trade-off necessary? It turns out that it is. And so we prove a matching lower bound showing that any 1 plus epsilon consistent randomized algorithm for measurable task systems is exponential in 1 over epsilon robust. And the proof idea here is we construct a particular metric space in a particular problem instance where the advice doubles its distance from the robust algorithm decision at every step. And then any 1 plus epsilon consistent algorithm has to be bounded in how much probability mass it sends back to the robust decision. And so what this looks like is sort of our algorithm or any algorithm and the advice in the robust start at the same position. This bar is the probability mass of the algorithm at a particular location. And so in the first time step, the robust moves to the left and the advice moves to the right. And so our algorithm has to be 1 plus epsilon consistent, so sends just a little bit of mass back. And then the advice keeps on getting further and further away, doubling its distance at each time. And by the time you've sent all of the probability mass back to the robust, you've moved exponentially far away. And so in particular, after order 1 over epsilon steps, you've moved exponentially far away in 1 over epsilon. And it turns out that we can also get the same lower bound in the convex function chasing or convex body chasing setting. So it's not just this contrived metric space, but if we embed this metrical task systems instance into an L1 norm, we get the same result. And this construction is still a bit contrived. And so it looks like a sequence of planes in a weighted L1 space. And so I think there's an interesting question here, which is, this lower bound construction is very worst case and, very particular to the metric that we're using. Is this actually, the sort of trade-off that you see in practice? It's not. And so there are actually many cases where we can do better than this exponential trade-off. And then also in practice and in experiments, we never really see this behavior. But, figuring out more quantitatively why there's such a sort of brittle trade-off here in the worst case is an interesting question. But so for certain metrical task systems problems, Dart can perform better. And so we show that if the decisions made by the advice and the robust at every time step are always bounded in distance, then we get a trade-off that's just Dart being 1 over epsilon robust with some additive term that depends on d over epsilon. And there's a comparison here to the Antoniades result where they also had this sort of 1 plus epsilon and then d over epsilon guarantee. In the Antoniades algorithm, they needed to know the diameter in advance. The algorithm doesn't need to know the diameter. This is sort of a post hoc guarantee that you run the same algorithm and this guarantee holds. And in addition, this diameter term is only for the robustness. So you still get your pure 1 plus epsilon consistency. And in addition, there are other problems. So for the K-server problem, which is a problem of great interest in the TCS community, Dart can achieve 1 plus epsilon consistency and K over epsilon robustness. And this follows by the fact that for any valid K-server algorithm, you can always bound the distance between any 2 algorithms by K times the optimal cost. All right, so that's it for theoretical results in this section. Now I'm going to shift gears and talk a little bit about applications. So in a lot of my work, as I've mentioned, we think about energy system operations. And so one of the applications we've thought about is cogeneration. And in particular, we've worked with a company called Beyond Limits, which is based in Glendale, that does a lot of consulting for companies in the energy and power space. And they've been working with a company on optimizing the operation of electricity and steam cogeneration at a municipal level. So in the setting, you have a cogeneration plant, and then you also have some variable renewables or wind on the grid. And you want to optimize the operation of your plant, minimize fuel costs, make sure that you're satisfying constraints, meeting supply-demand balance, while also not ramping too much. And the ramping in particular gets hard because as there's more renewables on the grid, that necessitates more frequent and more significant ramps. So we can model this as a metrical task systems instance where the decision space is some n-dimensional vector space. The decisions are something like all of the dispatch set points for steam and energy and all of the switches for the plant. And the switching cost is ramp cost. And then the cost function is something like the fuel cost of generation under whatever ambient conditions, wind, sun, temperature, humidity. And as I mentioned, the decision includes power and steam generation for all trains of the plant. And the switching cost reflects cost of ramping, which results from degradation or increased inefficiency of operation, so forth. So the learning-augmented algorithm setup that we use for this application is sort of motivated by the fact that real-world fuel costs are often non-convex. So in simple economic dispatch applications, you just have convex cost functions, but we're using a real plant model for this cogen plant. And so depending on what dispatch set point you have, there will be different thermodynamic behavior in the plant, and it's really hard to get a closed form interpretable model for what's happening and what the costs are. And so we assume that the fuel costs are non-convex and highly complex, and so it's not possible to do something like just solve model predictive control in real time. And so instead what we do is we train a machine learning algorithm as our advice to choose our dispatches. And you can do this in multiple ways. You could train an ML algorithm in a sort of regression fashion based on dispatches that you've already computed, or you could train it in more of a task-based way where you just train an RL algorithm to choose dispatches based on conditions. Many different ways to do this. And then we combine this algorithm with our robust algorithm, which is just a greedy baseline that minimizes the current fuel cost and is agnostic to the switching cost. And we're able to show that, not unexpectedly, doing the machine learning approach significantly speeds up computation time for generating these dispatches compared to doing something like model predictive control. Because we don't have to solve some multi-time step non-convex optimization problem. Instead, we've done all of the hard part offline in training the model, and then we can just run it in a feed-forward pass online. And moreover, we're able to really take advantage of the guarantees given to us by the learning-augmented algorithm setup. So here in blue is the machine learning algorithm. In green is Dart, and in orange is the greedy algorithm, where the x-axis is something like distribution shift or noise added to the predictions fed into the machine learning model. And so you can see that as the noise or distribution shift increases, machine learning algorithm performance degrades, which is to be expected. The greedy stays the same because it's not taking into account any of these predictions or any of the underlying distribution. And Dart is really able to smoothly interpolate between the performance of the ML when there's no distribution shift and the greedy algorithm when there's a lot of distribution shift. And so this is nice because even though we have these very pessimistic worst case bounds, in practice, Dart and other learning augmented algorithms typically perform much better. And moreover, the benefit of using machine learning and learning augmented algorithms increases as wind penetration increases. And so on this plot, the x-axis is increasing wind penetration, and the y-axis is normalized cost. And so as wind penetration increases, ML performance increases, and also Dart's performance increases. And it's even better than just the pure ML. And I think the takeaway here is that when using a learning augmented algorithm, it can sometimes do better than both of the component algorithms that you fed it. Because if it learns soon enough sort of which regime it's in, then it can exploit that. And it doesn't have to just be equal to the better performance like in aggregate. It can really be instance dependent.
Learning algorithm, what does it take as input? Does it take the wind conditions right now, or is it?
Yeah, so the learning algorithm in this setup takes wind conditions over some look-ahead horizon. So predicted wind conditions over some look-ahead horizon.
And the cloudiness of the sky and things like that?
It's wind speed, temperature, pressure, humidity, and electricity demand. All right, so some
Sorry, quick question. So what's the control frequency here?
sorry,
So how frequently do you send an action?
every 15 minutes.
Okay.
So it's more of like an economic dispatch style problem rather than like a high frequency regulation problem. All right, so just to provide some concluding thoughts about Dart. So we're able to achieve the optimal exponential consistency robustness trade-off for general metrical task systems. We can get better trade-offs for certain subproblems. And there are some interesting questions that I think are motivated by this work, where in the experiments, we can see that Dart is really able to take advantage of the better performance of either the robust algorithm or the advice algorithm that is provided. And there's also an aspect of Dart being able to do well, not just for this pessimistic exponential worst case, but also when there's bounded diameter, and also when we're in the K-server problem. So this is a sort of ill-posed question, but I wonder whether Dart is optimal in an instance-dependent sense. So if you feed it a new MTS, is Dart optimal for that MTS? It's an interesting question. Another question is, how brittle is the exponential lower bound? So as I mentioned, it's a very particular metric space where we can generate this lower bound. And so it'd be interesting to examine, if you look at special classes of problem instances or make additional assumptions, does this lower bound show up? And related to this, are better bounds possible in certain metrics? So that lower bound works in something like an L1 metric, but I have a conjecture that in an L2 metric, it's probably easier, because in L2 you can sort of short circuit or shortcut movement. And so yeah, I don't exactly know how that proof would go, but I think that's a very interesting question. And then more generally, I think there's a lot of interesting questions around how do we get learning theoretic guarantees for these prediction algorithms in the first place? So there's a recent line of work on learning predictions for problems like ski rental and caching, things like that. Metrical task systems is a bit more difficult because it's a multi-step decision-making problem, but it'd be interesting to get sort of guarantees on how do you actually learn optimal algorithms for MTS from data. And how can you do this in a way that is aware or proactive to distribution shift, or that is generating uncertainty estimates, something like that. And as a brief aside, it's worth asking what other problems can we solve with learning-augmented online optimization? And so another problem that I have thought about quite a bit is data center operation. And you can model this in some form, like metrical task systems with a long-term constraint. So in this case, you're thinking about the costs being something like the cost of operating a certain number of servers and meeting your job demand. The switching costs are the costs of migrating jobs from one data center to another, or switching servers on and off. And the long-term constraint is the tangible constraint that you need to get your jobs done within a certain time horizon. And this is just a mathematical formulation of this problem, where you have your costs for having a certain decision at each time step, you have your switching costs, and then you have a long-term constraint. And in particular, we've thought about this problem where the cost that you see at every time step is something like a carbon cost, and you're trying to minimize your overall carbon emissions for operating your data center, while also meeting your long-term job demand. And we have some work, including work in Sigmetrics this past year, actually just a couple weeks ago, where we designed competitive and learning-augmented algorithms in this setting as well. And the key idea is very similar to the Dart approach, where you take a weighted mixture of your advice and some robust algorithm, And this is able to give you competitive like robustness and consistency guarantees. So this is a very powerful idea that works across many different problems in online optimization. All right, and as an interlude, I'm just going to briefly plug SustainGen, which is a suite of reinforcement learning environments that we had in the NeurIPS datasets and benchmarks track this past year. The Cogen environment that I mentioned and the experiments is one of the environments, and we also have an EV charging environment using real-world data from Caltech, an electricity market environment, a data center operation environment, and a building operation environment. And so if you or anybody that you know are working on RL or decision-making algorithms in general, please check out SustainGen, test your algorithms. I think there's a lot of really interesting questions related to operation and control in these sorts of complicated domains. And so in particular, there's a lot of constraints that you have to satisfy in these sustainability-related applications. There's distribution shift that you have to deal with. There's mixed, discrete, continuous decision spaces. So I think, this suite of environments really motivates a lot of follow-up work on designing algorithms for learning and decision-making in these complex settings. So check it out. And then for part 1.5, I think I'm at 45 minutes past the hour, but I'm just going to keep on going. This is short and more speculative and just initial steps. So please especially interrupt me during this part. I'm going to talk a little bit about going beyond black box advice using uncertainty quantification. So in all of the previous work that I've discussed, we're really assuming that the advice that we receive at each time step is adversarial, or at least it can be adversarial. And this is what gives us the very pessimistic, exponential trade-off between consistency and robustness. But in practice, machine learning usually performs much better. And maybe there's something else which is sort of giving us the bad performance. So maybe there's distribution shift or covariate shift, which is making our model perform worse. Or maybe there's an adversary perturbing our inputs or something like that. And this sort of motivates using more modern techniques for machine learning in order to go beyond just point predictions or go beyond just a black box model of what machine learning is giving us. So in particular, modern machine learning gives us methods for doing uncertainty quantification, so we can tell how certain or uncertain our model is about the decision that it's making or the prediction that it's making. And so this motivates the question of, can we leverage this uncertainty quantification in domains where our advice is not just telling us a decision that we should make, but it's also telling us a confidence with which we should make that decision. So if our advice tells us, I'm confident you should play the decision AT, or it says, try playing AT, but I'm not totally sure, we should probably design our algorithm to respond differently to those different scenarios. And so a motivating motif here is in convex body chasing, where if we receive a convex body and then we see a predicted decision that we should make, maybe we also get an uncertainty ball, where our model is telling us move here, but also maybe the optimal decision is in this ball. And so if we're faced with this sort of a decision-making scenario, how should we use this uncertainty quantification to make decisions optimally? And can we get bounds that actually improve based on good uncertainty quantification? So one test setting where we have explored this and have some initial results is for the ski rental problem. And this is more of a toy online algorithms problem, but it's actually an important building block for more general online optimization problems. So ski rental is like the foundation for more general metrical task systems. And so we're faced with an unknown adversarial chosen ski season duration S, which is a positive integer. And buying skis costs $B, whereas renting costs $1 per day. And we're faced with the question of how long should we rent skis before buying them in order to minimize our competitive ratio? Because the adversary, maybe as soon as we choose to buy skis, will choose the ski season to end on that day. And so in particular, if we buy at the start of day X and X is less than the ski season duration, then our cost will be B for buying plus X minus 1, since we rented up until day X. And on the other hand, if X is greater than the ski season duration, we just pay S because we've rented exactly for the entire duration. And so the competitive ratio of a deterministic strategy that buys at time X is just the worst case over adversary decisions in the natural numbers of S times the indicator of our decision being greater than S, plus B plus X minus 1 times the indicator of X being less than or equal to S, divided by the offline optimals cost, which is S if it's smaller than the buying cost, or B if the duration is greater than the buying cost. And so there's a lot of classic work on designing algorithms for ski rental. And so in particular, if you just buy deterministically on day B, this gives the optimal deterministic competitive ratio of 2 minus 1 over B. And randomization can improve this competitive ratio. So if you buy at a random time X between 1 and B with a probability mass function proportional to this function, which is sort of exponential, then your competitive ratio approaches E over E minus 1, or 1.58, as the buying cost grows large. And just as a tangent, this randomization actually introduces risk. So if you randomly choose which day you buy on, it might be that you buy on a very early day, but then the ski season duration might be very short. And so you might have a large empirical competitive ratio with a small probability. And this is what our paper at Colt was about this year. So I encourage you to take a look at it if you're interested in that sort of theoretical work. So we're faced with the question of how should we evaluate algorithm performance when we have uncertainty quantified predictions. So uncertainty quantification gives us some information about distributions over instances. And we want to balance between the case where our UQ is right versus it's wrong. Because typically it'll be some sort of probabilistic guarantee where with probability 1 minus delta, the prediction is in some range. And so one metric that we have come up with is called the distributionally robust competitive ratio. We're given some uncertainty quantification data theta about the true distribution of problem instances. The distributionally robust competitive ratio, or DRCR, of an algorithm is the worst case expected competitive ratio of our algorithm compared to the offline optimal, where the expectation is over the worst case distribution characterized by this UQ data. So the uncertainty quantification tells us something like the true instance is between L and U with a certain probability. That characterizes an ambiguity set of distributions from which the sort of true instance can be sampled. And we're looking at the worst case expected competitive ratio of all of these possible distributions. And the UQ model that we use for ski rental is very simple. The standard approach is just to use a black box prediction of the true number of skiing days or of the ski season duration. And we have two different generalizations that we can think of. One is just a probabilistic point prediction. So you have a prediction that the true season length is P with probability 1 minus delta. And then more general and more connected to uncertainty quantification in practice is a probabilistic interval prediction, where we predict that the true season length lies in some interval LU with probability 1 minus delta. And so then if we are faced with this type of uncertainty quantified prediction, the DRCR for ski rental turns into something like this, where it's a weighted sum of two supremums. The first is the case, which happens with probability 1 minus delta, that our prediction is correct. So with probability 1 minus delta, you're taking the worst case adversarial ski season duration in the interval L to U, and the competitive ratio in that case. And then with probability delta, you're just looking at the worst case problem instance. And so this is just computing the expectation from that distributionally robust formulation. And so the second line is just filling in the costs for the ski rental, and we define eta to be the consistency that an algorithm gets, and gamma to be the robustness that an algorithm gets. And so faced with this definition of the distributionally robust competitive ratio, we can ask, how do we design optimal algorithms for ski rental when we have these probabilistic interval predictions? And so we're able to provide an optimization-based algorithm design framework where we're directly optimizing the DRCR over the space of all possible algorithms. And what this looks like is you just have the DRCR in the objective. So this is just 1 minus delta times the consistency plus delta times that worst case robustness. And then you add as constraints to the problem the consistency condition, which says our algorithm should be eta consistent in all of the cases where the UQ prediction is actually correct. And then it should be gamma robust otherwise, so in the worst case. And it turns out that this is the way to get the optimal strategy for ski rental with UQ predictions. And moreover, for ski rental, we can reformulate this problem as a finite linear program, so it's actually tractable to solve. So this is all fine and good, but it's just a ski rental problem, a very toy TCS problem. But it does turn out that the optimization-based design framework can apply to some other problems. So we also look at an online search or one-way trading problem. But there's also another question which I think is important and which I don't know how to solve. It's something that I'm still thinking about. But what should we do in multi-instance or multi-time step settings, or if the UQ isn't worst case? And so one thing that we can do is learn how to leverage UQ optimally using online learning, and that's something else that we do in this paper, where the purple here is just the standard DRCR optimization-based approach, and then this red and green curves, which slope downward, are online learning-based approaches, which sort of learn over time how to optimally use the UQ. But more generally, if we're faced with something like metrical task systems, it's not entirely clear what you should do with that sequential uncertainty quantification information. And I think that's an important and interesting question. And moreover, what I've presented so far is sort of a two-step framework where we have some model with uncertainty quantification provided, and then we're using that uncertainty quantification to make decisions. But why should we learn the UQ separately from doing the decision-making problem? And so this connects to this observation from the machine learning literature that minimizing prediction error doesn't always translate to good downstream performance. And this motivates the idea of task-based learning. And so there's a really great paper by Priyadanti from 2017 called Task-Based End-to-End Model Learning and Stochastic Optimization, where she and her co-authors basically looked at if you're predicting, say, electricity demand, and then operating a economic dispatch model based on that predicted electricity demand, minimizing the root mean square error doesn't necessarily give you optimal performance. Because in electricity market operation, it's better to overpredict demand than underpredict. Because if you overpredict, then you've over-provisioned the amount of resources that you need. But if you underpredict, then you're going to have a resource shortage, and that's very, very costly. And so these asymmetries in terms of what you're predicting and what types of errors matter more are really important for decision making. And so in reality, we should be training our models based on whatever the downstream task loss is. And this is also true for uncertainty. So different types of uncertainties are better or worse. And so maybe you should care more about the sort of high tail of uncertainty, or maybe you should care more about the low tail of uncertainty. But in general, we have sort of proposed that you should try to learn your uncertainties in a way that is aware of the downstream decision problem. And so how should we train models with uncertainty quantification to optimize this downstream performance? Well, we have some preliminary work doing end-to-end training in this setting for a robust optimization problem, where we have some ML model which is parameterizing uncertainty somehow. I'm not going to get into the details, but we're actually able to train calibrated machine learning models with calibrated uncertainty to provide uncertainty sets for robust optimization in a way that takes advantage the sort of downstream task loss. So we propagate gradients from the downstream loss all the way back to the model training, and we do this in a way that preserves calibration of the model all the way through training. So you're always learning over well-calibrated models. And in particular, this is made possible by differentiable convex optimization. So there's been a lot of work in the last 5-8 years on this. And then also differentiable conformal uncertainty calibration. And just as sort of a teaser, these results from our preliminary work show that there is a benefit to doing end-to-end learning in this manner. So here the ETO is a framework that's just estimate then optimize, where you're estimating some uncertainty set and then running your optimization problem. Whereas the E2E is an end-to-end framework where we're really learning the uncertainty in a manner that's aware of the downstream loss. And we see pretty significant drops in terms of the loss when moving from the estimate and optimize to the end-to-end, while maintaining good coverage or good calibration of our models throughout. Yes?
So I'm assuming that this is very dependent on the robust optimization problem that you have. In general, the gradients of an optimization problem may not be defined or even meaningful, right? So I'm assuming that this is for you essentially define the optimization problem such that the gradients are giving you information that you can use down the road, right?
That is correct. So for this framework in particular, you are restricted to solving convex optimization problems.
Is it a quadratic problem?
I think you can do. I think you could do any sort of convex optimization problem.
For linear problems, most of the time, linear programs do not have informative or meaningful gradients.
It depends what you're trying to differentiate through. So if you're trying to differentiate through the objective, then it won't have a meaningful gradient. But through the parameters, you can get meaningful gradients. Yeah.
But how do you calculate that gradient? To propagate back to the training problem.
Right. So mathematically, there's a way that you can write out the KKT conditions, and then if you solve the optimization problems, you do something like invert the KKT conditions in order to compute gradients. Practically, there's a Python package called CVX PyLayers, which will just do this automatically. And it works with PyTorch, and you can just implement this in your code.
Okay. I assume they're doing some sort of like kind of perturbation sensitivity analysis.
Yeah, I mean, at its core, it is a sensitivity analysis, but it uses the KKT conditions of optimality in order to compute the gradients. Yeah. All right, so that was sort of just a teaser about this direction. But to conclude, we give optimal robustness consistency trade-offs for MTS. We have started to explore how uncertainty quantification can improve performance. And there's also this observation that if you want maximal benefit for using uncertainty quantification, or really for any sort of machine learning algorithm, you should be training end-to-end. And I think there are some really interesting open research directions that this leaves. So specifically, how can we incorporate uncertainty quantification in more complex or more complicated online algorithms problems? So I just showed results for ski rental, but ski rental is not very applicable in practice. So it'd be really great to get some results for metrical task systems or online allocation or other types of problems. And then on the other side, I think going beyond like the robust optimization type framework for the last work that I mentioned, convex optimization problems are very useful, but there are a lot of problems that aren't convex. So can we do anything there? Dealing with risk or distribution shift or hard constraints or all of these other considerations that you have to think about in practice, I think are very important, especially because if you train a model on some set of data, in practice, there's going to be some sim to real gap. So how can you characterize that or sort of proactively account for that in your algorithm design? And then going beyond online problems. So I'm really motivated at core by getting worst case guarantees on machine learning algorithms. And so thinking about other problems in energy system operations, like classification problems for contingency analysis, things like that, all very interesting. And I think there's a lot to learn from the online algorithms community and the optimization community and the machine learning community. Anyways, that's my talk. Thank you all for listening, and happy to take any more questions.
Any questions? So thank you for the talk, very interesting results. So I'm curious if you guys have studied the case where the machine learning model that provides advice that is being trained in an online fashion. So for example, in the continual learning setting, right? And this is a little bit different from like shifts that we have in your data set because obviously that's one specific case. But the other problem is that your model becomes more and more accurate, and then this depends on the decisions that you make. So if you consider the control problem that you mentioned as one of the examples here, right? In the control problem, your decision-making agent will affect the distribution of the result, and as a result, everything will change. Have you looked into this?
I haven't looked into that, but that sounds like a very interesting direction. Especially because online, especially if there is distribution shift happening, presumably, one way to get robustness is to have some sort of robust and consistent algorithm set up. But another way is to just continue training your model so that it incorporates that new data that you've seen. And so I think there's, different regimes depending on the timescales of learning and decision making. I think the robust and consistent approach works if you're in a short time scale and you want worst case guarantees. But if it's okay for you to not have those guarantees over some intermittent period in order to do better learning over the long run, I think doing some sort of continual learning does make sense.
So at times you'll intentionally make the wrong decision.
Sorry?
Or at times you'll intentionally take the action which you think is not optimal.
Right.
Yeah,
Right. Yeah, and I think in that realm, sort of this idea of exploration versus exploitation connects with bandits, which is another area that I haven't worked on, but I think there could be some interesting connections with bandit algorithms, thinking about combining machine learning and robust approaches. Yeah.
Something similar. So you're talking about when with ML model you have this uncertainty quantification. If somehow these ML advice is not correct in the current round, but it gives information about like a good decision, can we somehow incorporate it? Because like this happens in bandit. Like the current action is not good, but then it gives information about the good action.
So do you mean like an action that's suboptimal now, but that will set you up for a better performance later? I think there's some extent to which that can also happen in MTS type problems, because an advice algorithm might tell you to move very far right now, and that might look locally suboptimal. But then over the long run, it might turn out that, oh, that's actually the minimizer of all the future cost functions.
You showed that picture.
Sorry?
You showed that picture where the second jump would have been not from yours point, but it pointed to me.
Right. Right. And so, yeah, I think that can happen. Reasoning about that in sort of a theoretical way to figure out like whether that changes the trade-offs, though I haven't thought about.
Yeah, because usually there is some information theoretic quantities involved. You want to measure the like how much information you're gaining from the current decision. And in the DART algorithm that you showed, it was like there was no such quantity. But if it's still able to do that, then it's kind of interesting.
Yeah, that would be interesting. I'd have to give that a bit more thought.
For your like cogeneration application, could you like talk more about the performance of MPC?
Yes, I don't think I have a figure on that, but
Just like how did it compare to DART?
yeah. So I mean, MPC and the MPC and the ML performed essentially identically. So the ML here is basically just interpolating the MPC decisions. So training some sort of proxy to the optimization problem being solved by MPC. And so MPC would also be impacted by this distribution shift because the distribution shift is on predictions being provided to the decision-making algorithm.
Is there a recent like structural property that makes it easier to work with as like incorrect interval with probability 1 minus delta versus it seems like maybe a more rich output of your prediction would be like happen?
Yeah, that's a good question. I think the reason we use the model of the probabilistic interval prediction is because that's very common in the UQ literature, and that's something that you can get from like conformal prediction, for example. I think it's a bit harder to get something like a calibrated probability distribution, and it's not clear to me like what that would exactly mean. You might be able to get a good estimate of what the distribution is, but how do you like model or enforce guarantees that it's actually like correct with a certain probability or something like that?
Any other question?
You're around a little bit after this?
Sorry?
You're around for a few minutes after this?
Yes.
Okay, if there's no more questions, then let's give our speaker another quick look. Thanks.